This presentation is delivered by the Stanford Center for Professional Development.
All right, so today I want to continue our study and begin a serious mathematical study of the question of periodicity. Remember that we are essentially identifying the subject of Fourier series with the mathematical study of periodicity. And last time I went on at some length about the virtues of periodicity, about the ubiquitous nature of periodic functions, periodic phenomena in the physical world and also in the mathematical world. And we made a distinction, perhaps a little bit artificial, but sometimes helpful, between periodicity in time and periodicity in space. The sort of two phenomena seem to be or often come to you in different forms, and it's sometimes useful in your own head to sort of ask yourself which kind of periodicity are you looking at. But in all cases, actually, periodicity is associated with the idea of symmetry. That's a topic that will come up from time to time, and if I don't mention it explicitly, as with many other things in this course, it's one of the things you should learn to sort of react to or think about yourself. See what aspects of symmetry are coming up in the problem. How does a particular problem fit into a more general context? Because, as I've said before, and we'll say it again, one of the wonderful things about this subject is the way it all hangs together and how it can be applied in so many different ways. All right, if you understand the general framework and orient yourself in a certain way, using the ideas and the techniques of the class, you'll really find how remarkably applicable they can be. Okay? So, as I said last time, as we finished up last time, when we were sort of still just crawling our way out of junior high, a mathematical approach to periodicity is possible because there are very simple mathematical functions that exhibit periodic behavior, namely the sine and the cosine. But that's also the problem, because periodic phenomena can be very general and very complicated, and the sine and the cosine are so simple. So how can you really expect to use the sine and the cosine to model very general periodic phenomena? And that's really the question I want to address today. So how can we use such simple functions, sine of t and cosine of t, to model complex periodic phenomena? Now, first, a general remark is, how high should we aim here? I mean, how general can we expect this to be? So how general? All right, that's really the fundamental question here. And in answering that question led both scientists and mathematicians very far from the original area that they were investigating. Let me say right now, pretty general, all right? And we'll see exactly how general. I'll try to make that more precise as we develop a little bit more of the terminology that really that will apply and allow us to give more careful statements. But we're really aiming quite high here, all right? And we're really hoping to apply these ideas in quite general circumstances. Now, not all phenomena are periodic, all right? And even in the case of periodic phenomena, it may not be a realistic assumption. I think that's important to realize here what the limits may be or how far the limits can be pushed. So not all phenomena, naturally, although many are, and many interesting ones are periodic. And even periodic phenomena, in some sense, you're making an assumption there that is not really physically realizable. So even for periodic phenomena, or at least functions that are periodic in time, even phenomena, soon I think I'll start talking in terms of signals rather than phenomena, but phenomena sounds a little grander at this point. Even phenomena that are periodic in time real phenomena, that is, die out eventually. We only observe, or at least we only observe something over a finite period of time, whereas as mathematical functions, the sine and the cosine go on forever. All right, as a mathematical model, sine and cosine go on forever. So how can they really be used to model something that dies out? But a periodic function, sine and cosine, all right, go on forever, repeating over and over again. All right, so in what sense can you really use sines and cosines to model periodic phenomena when a real periodic phenomena when it really dies out? Well, that'll take us a while to sort all that out. Let me just give you one answer to this and one indication of how general these ideas really are. And you have a homework problem that asks you actually to address this mathematically. All right. Suppose if you have a finite, you can still apply ideas of periodicity, even if only as an approximation or even if only as an extra assumption. So what I mean by that is as follows. So suppose the phenomenon looks like this. Suppose the signal looks like something like this. Let me write it over here. So it dies out over a period of time. So this is time. And there's only a finite interval of time, might be very large, but there's only a finite interval of time when the signal is non-zero. I'm drawing it just as a somehow generic signal here. Well, that's not a periodic phenomenon. It doesn't exhibit periodic behavior. But if it dies out only after a finite, outside of a finite interval, then you can just repeat the pattern and make it periodic. Right? Force this. You can force periodicity. That is by repeating the pattern. You can force extra symmetry. You can force extra structure to the problem that's not there in the beginning. So I mean by this a very simple idea. Here's the original signal, and I just repeat the pattern. So this is the original signal. These are maybe sort of, extra copies of it that I'm just inserting artificially and extend the function to be periodic and exist for all time. You may only be interested in this part of it, but for mathematical analysis, if you make it periodic, that'll apply to the whole thing. All right? This is sometimes called the periodization of a signal. And it can be used, and it is used, to study signals which are non-periodic to use methods of Fourier series, in some cases other sorts of Fourier analysis, to study signals which are not periodic. So there's actually a homework problem on different sorts of periodization, and it's a technique that comes up in various applications. All right, so see the first problem set, homework 1. Now, the point is that periodicity and the techniques for studying periodic phenomena are really pretty general. All right, even if you don't have a periodic phenomena, you can make it periodic, and perhaps you can apply the techniques to study the periodized version of it, and then restrict to study the special case of actually where you're interested in the function. All right, so it's pretty, that's the point of this remark, is that the phenomena, that you're not restricting yourself so much by insisting that you're going to use sines and cosines or you're going to study periodic phenomena. So the study that we're going to make here can be pretty general, can apply really quite generally. Okay, now let's do it, or let's get launched into the program. So first of all, let's fix a period in the discussion. All right, so we just to specialize and fix ideas. Let's consider periodic phenomena of a given fixed period and see what we can say about those. See how we can model those mathematically. So for the discussion, let's fix the period for the discussion. All right, and there's a choice here. A natural choice would be 2 pi because the sine and the cosine are naturally periodic at period 2 pi. But I think for many formulas and for a variety of reasons, it's more convenient to fix the period to be 1. All right, so we're going to consider functions, signals which are periodic of period 1. So we'll use period 1. That is, we consider signals. I'll write things as a function of time, but again, it's not only periodicity in time that I'm considering. All that I'm going to say can apply to any sort of periodic phenomena. So we'll consider functions f of t satisfying f of t plus 1 is equal to f of t for all t. All right? And as the building blocks, as the basic model functions, we scale the sine and the cosine. That is, we don't just look at sine of t and cosine of t, we look at sine of 2 pi t and cosine of 2 pi t. So the model signals are sine of 2 pi t, that has period 1, and cosine of 2 pi t. That has period 1. All right, simple enough. Now, one very important thing I want to comment before we launch into particulars is that periodicity is a strong assumption, and the analysis of periodicity has a lot of consequences. If you have a periodic function, if you know it on an interval of length 1 and any interval of length 1, you know it everywhere. Because the pattern repeats, if you just know a piece of the function, you know it everywhere. So if we know, when I say if we know, if we analyze, if we whatever formulas we derive, and so on, this is an important maxim. So I'll put in quotes, know, to be a sort of generic, infinite, perfect, godlike knowledge. So if we know a periodic function, say period 1, on an interval, and not just a particular interval, but any interval of length 1, then we know it everywhere. All right. These are all simple remarks, okay? These are remarks that you all have seen before in various contexts, but again, I want to lay them out because I want you to have them in your head. And I want you to be able to pull out the appropriate remark at the appropriate time, and you'd be amazed how far simple remarks can lead in the analysis of really quite complicated phenomena. Now, how are we going to take such simple functions as sine and cosine individually and model very complicated periodic phenomena? That is, the sine and the cosine, as endlessly fascinating as they may be, are just the sine and the cosine. But the fact is, they can be modified and combined to yield quite general results. We can modify and combine sine of 2 pi t, cosine of 2 pi t, to model very general periodic phenomena of period 1, to model general periodic signals of, again, period 1. All right, now, here is the first big idea, or here's a way of phrasing the first big idea. When I talk about modifying and combining, well, let's first talk about modifying. And the maxim or the aphorism that goes with what I have in mind is one period, many frequencies. First big idea. One period, many frequencies. I think you can actually find this in the Dead Sea Scrolls. Okay, what do I mean, one period, many frequencies? Well, let me just take a simple example. I mean, for example, e.g., you have sine of 2 pi t, and we know what the graph of that looks like. I'll put the graphs over here. It repeats once. It's a period 1. It also has a frequency 1, that is, completes one cycle in 1 second. So if I think of this as the time axis, say, although I'm thinking in terms of time, it's a very general mathematical statement, it repeats exactly once on the interval from 0 to 1. All right? If I double the frequency and look at sine of 4 pi t, all right, then that completes 2 cycles. So this is period 1, frequency 1. Sine of 4 pi t is period 1/2, frequency 1, frequency 2, but period 1/2 also means period 1. All right, and the picture looks like this. It goes up and down twice. Does it? It does, in 1 second. All right, 0, 1. It repeats One cycle, it goes through one cycle in a half a second. It goes through 2 cycles in 1 second, so it's frequency 2. All right? But it also has period 1, because if you consider this as the basic pattern that repeats, then it also repeats on an interval of length 1. Okay, it's true that it repeats on an interval of length 1/2, that the signal is already contained in an interval of 1/2, but the signal also has a longer period. All right, has a shorter period, but also has a longer period. And let me do one more. If, for instance, I look at sine of 6 pi t, very simple. All my remarks are very simple. This has period 1/3. This has frequency 3, but it also has period 1. You might think of this as, I don't know, the secondary period, or somehow, I don't know exactly the best way of saying it, because really the best description is in terms of frequency, not period. And what does the picture look like? Well, this time it has 3 cycles per second, frequency 3, so that means it goes up and down 3 times in 1 second. See if I can possibly do this. 1, 2, 3. Good enough. 1, 0, and one cycle is it goes up and down completely once in 1/3 of a second, then the next third of a second it goes up and down again, the next third of a second goes up and down a third time. But it also has period 1, because if you consider this as the pattern that repeats, that pattern repeats on an interval of length 1. Although, in some sense, the true repetition, the true period, is shorter than that. Now, what about combining them? So that's how you can modify, and you do the same thing with cosine. That's how you modify the function. One period, many frequencies. If we combine them together, I actually have a picture of it here, but I think I'll just try to sketch it. Fool that I am. What about the combination? And when I say combination, I am thinking of a simple sum. That is sine of 2 pi t plus sine of 6 pi t, excuse me, sine of 4 pi t plus sine of 6 pi t. All right? What does the graph of that look like? Well, it looks like so. And I'm going to sketch this, and then I want to make another comment about this in just a second, but I actually had Mathematica plot this for me. It looks something like this. It goes, this is plotted on an interval of length 2. All right, I plotted it. And it goes, it's kind of nice. It goes up, and then a little bit like this. And then it goes up and then down a little bit farther, and up a little bit, then it goes down. That's the sound it makes. Up, down like that, and then up. Excuse me, that's not 2. It will be 2. And down and up, and then, there we go, 2. And then it repeats. Here's 1. All right, that's the sum. Now, what is the period of the sum? The period of the sum is 1. All right? Because although the terms of higher frequency are repeating more rapidly, the sum can't go back to where it started until the slowest one gets caught up, goes to back to where it started. All right? The period of the sum is 1. One period, many frequencies. There are 3 frequencies in the sum, 1, 2, and 3. But added together, there's only 1 period. So in a complicated, this is a very important point, and again, I'm sure it's a point that you've seen before. That's why I say 1 period, many frequency, and that's why for complicated periodic phenomena, it's really better, more revealing to talk in terms of the frequencies that might go into it rather than the period. You're fixing the period. You're fixing the period to have length 1, all right? But you might have a very complicated phenomena. That complicated phenomena, as it turns out, is going to be built up out of sines and cosines of varying frequency. As long as the sum has period 1, then we're okay. 1 period, many frequencies. That's the aphorism that goes on with this, that goes along with this. Now, in fact, we can do more than just modify the frequency. We can also modify the amplitudes separately, and we can modify the phases of each one of those terms. So to model complicated, perhaps, how complicated, we'll see. A complicated signal of period 1, we can modify the amplitude, the frequency, and the phases of either sines or cosines, but let me just stick with the sines, of sine of 2 pi t, and add up the results. That is, we can consider something like this. Something in the form, say, k going from 1 up to n, and we can consider however many of them we want. A sub k sine of 2 pi k times t plus, that's modifying the frequency, plus phi sub k, allowing myself to modify the phase, phi sub k. That's about the most general kind of sum that we can form out of just the sines, and I could do the same thing with cosines, or I can combine the two, and I'll say more about that in just a second. All right? So again, many frequencies, one period. All right? The longest period in the sum is when k is equal to 1, period 1. The higher terms, they're called harmonics because of the connection with music, and that's discussed in the notes, because simple sines and cosines model musical phenomena as a repeating pattern, musical notes. The higher harmonics, the higher terms have higher frequencies, have shorter periods, but the sum has period 1 because the whole pattern can't repeat until the longest period repeats, or until the longest pattern is completed. Now, I'm actually going to post on the website, I'm going to give you a little MATLAB program that allows you to experiment with just these sorts of sums, all right? That is, you choose n, it forms sums exactly like this. You can choose the a's, the amplitudes, you can choose the phases, and it will plot what a sum looks like, all right? It's called, so I have a MATLAB program with a graphical user interface. I wrote this myself, actually, a couple of years ago. It was the first thing I ever did in MATLAB. It was pretty clunky, let me tell you. But last year, a student in the class in 261 took it upon herself to modify it, which caused me to bump up her grade in the end. And it's really quite a nice little program, all right? And it's not complicated, but it'll show you how complicated these sums can be. All right, so as a MATLAB program, which I'll post on the website, sine sum, actually it's called sine sum 2 because sine sum 1 was my own version, which is now on the ash heap of history. All right, to plot these sums. And it's really quite, I mean, talk about fun, you know? I mean, to see how complicated a pattern you can build up out of relatively simple building blocks like this, it's really pretty good. So we're actually trying to see if we can do a homework assignment on the based on the program. There's a feature in the program that allows you to actually play the sound that's associated with this. That is, if you consider these things as modeling, if you consider the simple sinusoids as modeling a pure musical note, then a combination models a combination of musical notes, and if you put a little button plays sound, you'll get something that may sound good or may not sound good, but it's interesting to try. Unfortunately, the play sound feature doesn't seem to work on the Mac. It only seems to work on Windows. It requires Windows Media Player or something like that, Bill Gates' version of Death 4.2 or something. I don't know. Anyway, so we have to see if we can fix it to work on the Mac, but everything works on the Mac fine except for the playing the note. So I'll put that up on the web in a zip file, and you should fool around with it a little bit, okay? Because it'll give you a good sense of just how complicated these things can be. All right, now, so how complicated can they be? That's the question that I really want to address. I mean, this sum is already more complicated than just the sine and the cosine alone, but it doesn't begin to exhaust the possibilities that we want to be able to deal with. Let me say, to advance the discussion, actually, and to really get to the point where I can ask the question in a reasonable way, how general a periodic phenomena can we expect to model with sums like this? Let me say a little bit about the different forms that you can write this sum in, because algebraically, for algebraic reasons, primarily algebraic reasons, there are more or less convenient ways to write this sum. Okay? And I think it's worth commenting about it just a little bit. So different ways of writing the sum. The sum, this sort of sum. K equals 1 to n of a sub, I'll use capital in here. That doesn't matter. A sub k sine of 2 pi kt plus phi sub k. All right, now, you can lose the phase, so to speak, and write it in terms of sines and cosines if you use the addition formula for the sine function. That is the formula for the sine of the sum of two angles. So if you write sine of 2 pi kt plus phi k as the sine of 2 pi kt times the cosine of phi k plus the cosine of 2 pi kt times the sine of phi k, just using the addition formula, then that sum can be written in terms of sines and cosines. You can write the sum in the form, let me use for different coefficients, say sum from k equals 1 to n of little a k times the cosine of 2 pi kt plus little b sub k times the sine of 2 pi kt. All right? And you know how the little a k's and the b k's are related to the capital A's and the phase just by working it out. All right? So capital A sub k times this thing, and then there's a term coming from the phase. You haven't lost information about the phase in some sense. It's still there, but it's represented differently in terms of the coefficients, in the form of the sum. All right, this is a very common way of writing these sorts of trigonometric sums. Matter of fact, I'd say it's more common if you look in the applications, if you look in the textbooks, it's more common to write the sum this form than it is to write it in this form. But they're equivalent. All right, you can go back and forth between the two. And you can also allow for a constant term. You can shift the whole thing up. And that's also usually done for purposes of generality. Right? You can add a constant term. And it's usually written in the form a0 over 2. The reason why the a0 over 2 is in there is because of yet another form of writing it. Let me just write out the rest of it. a0 over 2 plus, again, sum from n equals, for k equals 1 to n of a sub k cosine of 2 pi kt plus b sub k sine of 2 pi kt. All right? And electrical engineers always call this the DC component. I hate that. All right? But they always do. All right? Who learned to call this the DC component? Yeah, I hate that. Not everybody. I'm glad to see that. That's because you think of a periodic phenomenon, you think about alternating. I don't know what you think about. You think of alternating current or voltage somehow as a periodic part, but then there's a direct part that doesn't alternate. There's a DC part, direct current part that doesn't alternate, and that's that term. The reason why I don't like calling this the DC component is because what if the problem had absolutely nothing to do with current? You know, you're sometimes trapped by your language, and the field, again, as I will say over and over again, is so broad and so diverse that you don't want to trap yourself into thinking about it in only one way. You know, you may be modeling some very complicated phenomena and you say, what is a DC component? And somebody's going to look at you like, what are you talking about? You know. All right, now, so that's a very common way of writing the form of the sum, but by far the most convenient way algebraically, and really in many ways conceptually, is to use complex exponentials to write the sum, not the real sines and cosines, by far. And this is pretty much the last time I'm going to use sines and cosines, or pretty much the last time I'm going to write the expression like this. So it's by far better. And I'll have to convince you of this, all right? Primarily algebraically, but also conceptually. It's by far better to represent sine and cosine via complex exponentials. And write the sum that way, all right? So what do I mean by that? Let me just remind you. of course, that e to the 2 pi I nt by Euler's formula is cosine of 2 pi nt plus, or k, I guess I'm calling it k. Let me stick with the terminology there. 2 pi kt plus sine of 2 pi k plus I times the sine of 2 pi kt. Oh yes, that's something else. All right. I'm going to announce a declaration of principle. I is the square root of -1 in this class, not j. Deal with it. Get over it. All right? For me, for this class, it's I. You can use j if you want. I will use I. Now, because of Euler's formula, Euler's famous formula, you can express sines and cosines in terms of the complex exponential and its conjugate. That is a very simple formula. The cosine is the real part and the sine is the imaginary part. So cosine of 2 pi kt is then e to the 2 pi I is the real part. 2 pi I kt plus e to the minus 2 pi I kt over 2. And the sine of 2 pi kt likewise is the imaginary part. That's e to the 2 pi I kt minus e to the minus 2 pi I kt divided by 2I. There is an appendix in the notes on the algebra of complex numbers. So if you're at all rusty on that, you should review that, all right? Because you're going to want to be able to manipulate complex numbers, and I'm thinking primarily here in terms of working with complex conjugates with real parts and imaginary parts. You're going to want to be able to do that with confidence and gusto, all right? So if you're at all rusty in manipulating complex numbers and complex exponentials, look over the chapter. All right. Matter of fact, on the first problem set, there are several problems that give you practice in exactly this, in manipulating complex numbers. All right, or complex exponentials. Now, because of this, and I won't write it out in detail, you can obviously then convert a sum, which is now gone, which looks in terms of sines and cosines, in terms of complex exponentials. So you can convert a trigonometric sum as before to the form sum, and I'll write it like this. Sum from k equals minus n to n, so it includes the 0th term, the constant term, c sub k e to the 2 pi I kt. All right? Where now the c sub k's are complex numbers. Everything in sight is complex. So, all right, the CKs are complex. Now, they can be, all right, they can be expressed. I won't do this, and I was going to give you a homework problem in this, but I decided not to. You can do this just for fun. You can see how the different coefficients are related. So start with the expression in terms of sines and cosines, make the substitution in terms of the complex exponential, and see what happens to the coefficients. All right? You will find actually a very important symmetry property. All right? These are complex numbers, but they're not just arbitrary complex numbers. They satisfy symmetry property, and it's because of the symmetry property that the total sum is real. All right? The symmetry property. This comes up a lot, and we'll see similar sorts of things reflected actually when we talk about Fourier transforms. That is, c sub minus, the sum goes from minus n up to n. They satisfy the property that c sub minus k is c sub k complex conjugate, ck bar. All right? That's a very important identity that's satisfied by the coefficients for a real signal like that, and it comes up often. All right? It's one of the things you have to keep in mind. All right, that's a consequence of actually making the conversion. That is, starting with a formula in terms of sines and cosines, and then getting the formula in terms of the complex numbers. All right. Conversely, if you start with the sum of this form, all right, where the coefficients satisfy the symmetry property, then the total sum will be real. That's because you can group a positive term and a negative term, and because of this relationship here, you'll be adding a complex number plus its conjugate, so you get a real result out of that. All right? So if the coefficients satisfy this, then the signal is real. Conversely, if the signal is real and you write it like that, then the coefficients have to satisfy the symmetry property. Yeah? What is that line? That line indicates complex conjugate. All right? So for a general, all right, do I have to say any more first? So for general complex number a plus bi, the conjugate is a minus bi. Okay? There are different notations for complex conjugates. Sometimes some people use different, some people use an asterisk, a star. Some people even use a dagger. All right, but I think by far it's true. I'm not making that up. But this is the most common notation. All right, and that is the notation that I will use. Okay, now. We are ready, at last, to at least ask the question that's really at the heart of all of this. How general can this be? How general can this be? I mean, I'm in the form now, algebraically, well, I'm in the form now where I can ask the question, and as we'll see, algebraically, writing sums of this form is by far the easiest way to approach it. So we can now ask the fundamental question, why is there something rather than nothing? Let's kick that one around for a while. The fundamental question, so again, f of t is a periodic function of period 1. All right, can we write it? F of t as that sort of sum, k going from minus n to n of c sub k e to the 2 pi I kt. So again, I'm assuming the signal is real here, so the coefficients satisfy the symmetry relation. Just keep your eye on the ball here. The fundamental question is this. You have a general periodic function. Can you write it as a trigonometric sum? Can you express it in terms of sines and cosines? Can you express it in terms of the fundamental building blocks? All right. By the way, linearity is playing a role here, although again I haven't said it explicitly until now. We're considering linear combinations of the basic building blocks. We're considering a linear way of combining the basic trigonometric functions, the basic periodic functions. All right, a linear way of doing that. So that's the fundamental question. And the answer, I'll tell you next time. But you don't think I'd make such a big deal out of it if the answer was no. So, but there's a lot to do. And answering this question led to a lot of very profound and far-reaching investigations. All right, now, but I want to get started on it. All right, now, let me give you a little clue. Yeah?
Like k equal to minus n to n, earlier you were starting with 1.
Why am I not starting with 1? Well, for one thing, so the question is, why does the sum go from minus n to n? And why doesn't it just go from 1 to n? Well, for one thing, if it went from 1 to n, the signal wouldn't be real, right? Remember, there's this combination of the positive terms and the negative terms, all right? And the positive terms and the negative term, because of the symmetry relation of the coefficient, the positive and the negative terms combine to give you a real signal, to give you a real part. And it's a fact that if you start with a real signal in terms of sines and cosines and then use complex exponentials to express it this way, you will find that it's a symmetric sum. It goes from minus n to n. Okay. By the way, I should have said something over here, I suppose. Note one thing, by the way, that c sub 0 is equal to c sub 0 is equal to c sub minus 0. 0 being what it is. C sub minus 0 is equal to c sub 0 is equal to c0 bar. What does it mean to say that a complex number is equal to its conjugate? It's real, all right? So the one coefficient that you know for sure is real, others may be real, it may just work out that way, but the one coefficient that you know is real for sure is the 0th coefficient, all right? So it must be real. So C0 is real. That's just a little aside. C0 is real, all right? You have to cut me a little slack here. Like I said, we all have to cut each other a little slack. There's so many little bits, to observe, little pieces, little comments and things like that. I can't make all of them, all right? I hope I put all of them or most of them in the lecture notes, all right, in the notes. So you see these things. But as I say, there's so many things along the way that you could point out, that you can note, that we just can't do it all because I want to keep my eye on the bigger picture. All right, but this is one thing that comes up often enough. So there'll be instances where you have to read the notes carefully and try to make note of all those things, and it's hard. It's hard. It's hard to know when you're going to need this little fact or that little fact because there's so many little facts. But you'll see when the whole thing, if you keep the big picture in mind, in many cases the details will take care of themselves. Really. Now, where was I? Yes, a secret of the universe. All right, here's a pretty big secret of the universe actually coming your way. When you try to apply when you're trying to see how mathematics works, and when you try to apply mathematics to various problems, you often have a question like this: how can something happen? All right, is it possible to write something like this? All right, now. A very good first approach, and I'm serious about this, when you're doing your own work and you're trying to look at a mathematical model of something, you're saying, can I do something like this? Often the first step is to suppose that you can and see what the consequences are. All right? Then later on, you can say, all right, then maybe I should try this because that seems to be what has to happen. All right? And then you go backwards. All right? And mathematicians will never tell you this because they like to sort of cover their tracks. They say, well, it obviously goes like this, and we're obviously going to define this formula and that formula, and life is going to work out so simply. But what they don't show you is often that first step of saying, suppose the problem is solved. What has to happen? All right? So suppose you can do this. We can write f of t equals the sum from k equals minus n to n of c sub k e to the 2 pi I kt. What has to happen? All right, now, by that I mean, if you can write this, what are the coefficients? If you can write an equation like this, then what I'm asking here is, what are the mystery coefficients in terms of f? Coefficient c sub k in terms of f is given to you. All right? So the unknowns in this expression are the coefficients. And the question is, can you solve for them? All right? Suppose you can write it like that. Can you solve for the coefficients? Can we solve for the ck? All right. I'm going to take a very naive approach. All right? I'm going to isolate. What do you do? Like an algebraic equation. Start with an algebraic equation. Isolate the unknown. So isolate like the, I don't know, mth coefficient or something like that. All right? So isolate Cm out of this. That is, it's a big old sum, right? So f of t is, all these terms plus c sub m e to the 2 pi I mt plus all the rest of the terms. That is to say, I can write c sub m e to the 2 pi I mt is f of t minus all the terms that don't involve m. So let me write it like this. Say sum over k different from m of c sub k e to the 2 pi I kt. All right? I haven't done anything except algebraically manipulated the equation to bring the one mystery term or one fixed term on the other side. All right? All I did here was, so f of t is this big sum. One of those terms in the sum is c sub m e to the 2 pi I mt. I want to solve for the unknowns. All right, so solve for the unknowns one unknown at a time. So this is the mth term in the sum. Bring that over to the other side of the equation. Write c sub m e to the 2 pi I mt is f of t minus all the terms that don't involve m. Okay? And then write that as, that's almost isolating c sub m, but not quite because it's got a complex exponential in front of it. So multiply both sides, this board is not so great, multiply both sides by e to the minus 2 pi I mt. So c sub m is e to the minus 2 pi I mt times f of t minus the sum over all k different from m of c sub k e to the minus 2 pi I mt times e to the 2 pi I kt. You with me? Nothing on my sleeve. All right? All right, now that's brilliant. I've isolated one unknown in terms of all the other unknowns. All right, so I don't know if one can say that we have really made progress here. So we need another idea. This is as far as algebra can take you. All right? Algebra says you want to solve for the unknown? Fine. Isolate. You know, what did your 8th grade teacher tell you? Put the one unknown on one side of the equation, put everything else on the other side of the equation, hope and pray. All right? So we put the one unknown on one side of the equation, everything else is on the other side of the equation, hope and pray. Now, the desperate mathematician at this point looking for something to do, let me actually take this out one more algebraic step. Let me just combine those two exponentials there and write this as C sub m is e to the minus 2 pi I mt minus the sum over all terms different from m of c sub k e to the 2 pi I k minus m times t. I'm just combining the two complex exponentials there. All right? Great. What?
F of t.
F of t. Picky. All right, f of t. Minus. All right, now, good. So now, they say that we need another idea. And the desperate mathematician, at this moment, will think of one of two things. You either differentiate or integrate. I mean, what's beyond algebra? Calculus. What's in calculus? Derivatives and integrals. All right? So here's a clue. Derivatives won't work, but integrals will. All right, we need another idea. And it's not a good idea. It's an inspired idea. It's an inspired idea because it works, and I'll show you why. So I'm going to integrate both sides. From 0 to 1. Over one period. All right? All I have to worry about here is one period. Everything's periodic at period 1. So I integrate over one, or I integrate from 0 to 1. What if I do? What do I get? Well, certainly if I integrate 0 to 1 of c sub m dt, that just gives me c sub m. All right? So what about the rest of it? So I get c sub m is equal to the integral from 0 to 1 e to the minus 2 pi I mt f of t dt minus the integral of the sum is the sum of the integral. Let me write this: sum from k, all the terms k different from m of, and the constant comes out, c sub k, the integral from 0 to 1 e to the 2 pi I k minus m t dt. That's a t there. T. Ouch. All right. I've integrated both sides from 0 to 1. All right. Now, watch this. All right. Watch. I can integrate that complex exponential. That's a simple function. I can integrate that just like I integrated in calculus. All right. The integral from 0 to 1 e to the 2 pi I k minus m t dt. Now, k is different from m. All right? If k is equal to m, I'm just e to the 0 here. I just get 1 again. So, but k is different from m. So the integral of this is 1 over 2 pi I. Trust me, integrating this is the same as integrating an ordinary function. 2 pi I as you did in calculus. 1 over 2 pi I k minus m e to the 2 pi I k minus m t evaluated from t going from 0 to 1. Straightforward integration. Straightforward integration. Which is equal to, we are almost done. We are almost there. One over 2 pi I k minus m. That makes sense, right? Because k is different from m, so that's not a problem. E to the 2 pi I k minus m times 1, so it's e to the 2 pi I k minus m minus e to the 0. All right? But e to the 2 pi I k minus m, that's e to the 2 pi I times an integer. That's like sine of 2 pi times an integer, cosine of 2 pi times an integer. That's 1. And e to the 0 is also better known as 1. So this is better known as 1 minus 1, which is better known as 0. Nothing. All this crap integrates to 0. Excuse me. All right? Incredible. What is the upshot? It all goes away. What is the upshot? The upshot is that C sub m, what's left? What's left is C sub m is the integral from 0 to 1. All the terms in the sum here are gone. Are gone. They've integrated out to 0. What remains is the integral from 0 to 1 of e to the minus 2 pi I mt f of t dt. All right? Now, in principle, this is known because you started out by assuming you knew f. Suppose I know f, what has to happen? All right, well, suppose I'm given f and I write f as this sum, what has to happen? Here is the answer. All right, here is the answer. Let me summarize. We have solved for the unknowns. All right, so given f of t, periodic, of period 1, suppose we can write f of t as this sum, k equals minus n to n of ck e to the 2 pi I kt. What has to happen? What has to happen is the coefficients have to be given by this formula. Then you must have, I'll just write c sub k instead of c sub m. The kth coefficient is the integral from 0 to 1 of e to the minus 2 pi I kt f of t dt. That's what has to happen. All right? So that's an important first step in applying mathematics to any given problem, whether it's a mathematical problem or a non-mathematical problem. Suppose the problem is solved, what has to happen? If the problem is solved, meaning suppose you have this representation, then the coefficients have to be given by this formula. All right, so next time I'm going to turn this around saying, suppose we give these coefficients by the formula, do we have something like that? And in what sense? And that will lead us to great things. All right, so more on that next time.